Good afternoon. I'm Dee Pack from the Aerospace Corporation. Our talk is entitled Landsat Imagery from a CubeSat, Results and Operational Lessons from the R-Cubed Satellite's First 18 Months in Space. I'd like to acknowledge my co-authors from our project's flight operations, science, and data processing teams. The R-Cubed mission had two main goals. First, collect Landsat-like imaging data from a CubeSat, and second, use the spacecraft's compact lasercomm system to transmit these data to the ground for analysis, processing, and comparison to Landsat 8 data. Some mission details. R-Cubed was a 3U CubeSat, i.e. when stowed, its dimensions were approximately 10 by 10 by 30 centimeters. Its visible near-infrared multispectral payload fit into less than 1.5 U of spacecraft volume. It launched on 16 December 2018 into a 500-kilometer circular 85-degree inclination orbit. In what follows, we will show you how we met our primary mission goals and present some imaging results. We will show that we generated Landsat-like multispectral data from a CubeSat, that we successfully downlinked the data via a 100 megabit per second lasercomm link. We also operated the R-Cubed spacecraft successfully for over a year on orbit. Chart 3 first shows a picture of our launch on 16 December 2018. Two photos of the completed R-Cubed spacecraft in the laboratory with its solar wings deployed are also shown. A nadir face view, where the multispectral sensor telescope and its small sunshade are prominently visible, and a zenith face view, where one of the two star sensors, a GPS antenna, and the spare RF antenna are visible. The fourth picture in this chart shows the compact multispectral payload in the laboratory prior to integration onto the spacecraft. Sensor parameters are shown in the tables, with the first table listing the R-Cubed bands, which are identical to the visible near-infrared Landsat 8 bands, due to our use of a spare Landsat identical filter. Other relevant sensor parameters are shown in the second table, including the R-Cubed swath width of 56 kilometers and the pixel resolution of 44 meters. Further details on the spacecraft and sensor are summarized in a small satellite conference paper from 2018 and in a 2017 CalCon conference presentation. In what follows, we present details of the spacecraft checkout and on-orbit multispectral imaging operations that led to successful generation of Landsat-like data. Chart 4 animates one of our on-orbit lasercomm boresight checkout experiments. The lasercomm system, a payload in its own right, was put through a series of on-orbit spiral search pattern tests, pointing at the Aerospace Corporation Laser Receive Station in El Segundo, California. These tests took place during March through April of 2019, following checkout of the spacecraft attitude determination and control system and initial sensor functionality tests. The figure and the related animations show a half-a-degree spiral-out search pattern boresight test. The camera data are from a signal strength measurement camera and illustrate when the signal peaks during the search pattern. These successfully executed boresight procedures allowed the spacecraft's mission-enabling lasercomm operations to begin in May 2019. Chart 5 shows our sensor's first light image, which verified that the sensor functioned and that the spectral filter survived launch. Payload focus and boresight tests were performed using the Moon and Venus. Short multi-frame data collects were downlinked via our UHF RF link, but for full testing and tuning of the multispectral sensor, we had to wait until our lasercomm system was aligned and in operation. The animated frame sequence shows raw data from a portion of an imaging swath. In what follows, we will describe how these data were used to tune sensor parameters to properly co-add successive frames and form time delay integration, or TDI, imagery. Chart 6 shows our multispectral imaging operations. The tasking, collection, processing, exploitation, and dissemination steps, plus the ground stations used to accomplish our mission. 5 automated RF ground stations handled satellite command and control and telemetry. Mission data were transmitted by laser and received via the single prototype laser receive station in El Segundo, California. R-Cubed was a testbed project for designing a data pipeline, and the processes we developed on the R-Cubed and the previous Cumulos missions are being utilized for follow-on prototyping programs. In Chart 7, we continue our discussion of our R-Cubed multispectral imaging operations. On the left is a chart illustrating 24 hours of imaging opportunities for the R-Cubed spacecraft. Due to star center constraints discovered on orbit, only certain times of day and solar conditions allowed the spacecraft to be used for precise, nadir-pointed operations without sunlight impacting the aft-mounted star sensors. The green dashed lines mark the options on each orbit. The coastal France target, selected by the operator, is highlighted by a green oval. The table on the right lists the dates, times, and sensor settings for imaging experiments. Chart 8 details how the focal plane is read out to form the time delay integration image. The spectral filter covers only a portion of the focal plane. All 1,280 focal plane columns are read out in the spatial dimension. 206 rows in the spectral dimension are read out and downlinked, and 114 rows are co-added and used to form the TDI images in the individual spectral bands. The filter was installed with a slant of approximately half a degree, slightly complicating our readout processing. 11 to 21 rows were co-added to form the TDI imagery in the 6 spectral bands. A single row image was also created to help visually assess blurring and aid in tuning the spacecraft yaw and the focal plane frame rate. Chart 9 shows an image chip of the South African border scene processed as both a single line scan image and as a TDI image. The scene has good terrain, river, and agricultural field features on which to test frame-to-frame image correlation. The TDI image chip is blurred, indicating the frame rate is not set properly. The plot on the right shows the excess motion in units of pixels per frame for both the in-scan along orbit direction, plotted in white, and the cross-scan direction, plotted in red. This analysis shows that the frame rate was too fast. The spacecraft orientation, or yaw, was about right. The noise and data dropout around frame 600 in the plot is from not having enough structure in that portion of the scene to track and correlate features. Chart 10 shows our third TDI test performed over a Greek coastal region. The pixel motion plot shows much less blurring is occurring for the settings used in this test. Images from each of the 6 bands are shown. The images are reasonably sharp and well exposed, with only the narrow coastal aerosol spectral band a bit underexposed. We were close to our optimal settings by this point and had developed our own procedures for checking out a push-broom spacecraft, which we assume must mirror some aspects of the Landsat program of record. Chart 11 shows the last of the TDI tests presented in this paper, an image chip from a 163 Hz frame rate experiment over northern Australia. Here we got the settings very close to perfect, with much less than 1/10 of a pixel drift, close to or at the limit of our analysis technique. The comparison of a single-line green band image to the equivalent TDI image shows no blurring and improved image contrast and signal-to-noise from the TDI process. The next charts study these data more closely and compare them to Landsat 8 imagery. Chart 12 shows the first step necessary for comparison of the R-Cube data to Landsat, georegistration. Individual spectral bands are georegistered, and an image cube is created from the overlap region of this short duration 1000 frame data collect. The data are on the coast of the Gulf of Carpentaria in Queensland, Northern Australia. The pictured red, green, and blue bands overlaid on a map imagery layer show the overlap region. With our R-Cube data georegistered, we can now compare them to Landsat. Chart 13 compares three standard multispectral products. Labeled A is a true color or red-green-blue image. Labeled B is a color infrared image, which is near IR red-green. The red color in the color infrared imagery highlights heavily vegetated regions because vegetation is strongly reflective in the near infrared. Labeled C is a normalized differential vegetation index, or NDVI image. NDVI imagery highlights the difference between the near infrared and red bands. Because vegetation is bright in the near infrared and absorptive in the red, higher values of NDVI highlight healthy vegetation, white in this image. The CubeSat and Landsat images are quite similar in these initial multispectral comparisons. The comparison between the R-Cubed and Landsat multispectral products is more easily examined in the next two charts, which magnify the data a bit. Toggling between these two charts, 14, the R-Cubed CubeSat, and 15, Landsat 8, shows close but not perfect agreement. The two images were taken at different times of day, almost 4 p.m. in the R-Cubed CubeSat data and 10:41 a.m. for the sun-synchronous Landsat 8 sensor data, taken 6 days later. Some features evident in the R-Cubed NDVI data appear to be due to afternoon shadowing. Other differences are discussed in more detail in the paper. Chart 15 summarizes the R-Cubed project. The R-Cubed mission implemented a custom refractive optic multispectral imager that compared well to Landsat 8. The mission was enabled through successful, repeated 100 megabit per second lasercomm operations. R-Cubed was a pathfinder for our CubeSat program's ground calibration, on-orbit TDI imaging checkout, radiometric and metric data pipelining, and data distribution efforts. Regrets included our lack of calibration collections, pseudo-invariant site measurements, calibration star observations, and repeated true Landsat conjunction collections. All these regrets are related to our weather-influenced lasercomm operations. And this will be helped for future projects by plans to add more ground receive stations. Despite spacecraft and ground station operational limitations, all the major program objectives were achieved, and the spacecraft operated successfully for 13 months on orbit. Thank you for listening. I look forward to discussing our work during the session webinar and to seeing my colleagues, hopefully in person, at next year's SmallSat conference. Acknowledgements. This research was funded by the Aerospace Corporation's Independent Research and Development Program. I'd also like to thank all of the organizers of the 2020 SmallSat conference for their hard work in pulling our conference together. Thank you very much.